So welcome to our session today on beginner statistics in ARM. So typically this is a 4 different sessions that we carry on through in the fall, at least here in the Northern Hemisphere. Each year, trying to maybe squeeze everything into 1 hour. So I'll go somewhat quickly. One of the reasons for this, of course, scheduling wise, we can cover some other topics in our webinar sessions then moving forward. But also one of the reasons is we have condensed all of the topics we usually do in these webinar sessions into shorter tutorial videos. And so we have a course out on our website. Let me just drag that down real quickly here. You can find that on our website underneath the video tutorials section in the resources on beginner statistics with ARM. So kind of everything that we're covering today, fairly quickly, all those talking points. We won't actually spend much time in ARM at all. I've got everything in slides and just have some screenshots. You're invited to either watch our previous webinars from like last year or the year before, where we go into each of these topics in a lot of detail, show ARM, talk through the tool, things to consider. Or you can also watch these videos here, a little bit shorter. They're more pithy, more to the point on those examples. And about 40, I think it's 41 minutes or so of playtime there throughout those videos. So that's kind of our main motivation for shrinking things down. Also, just as time goes on, of course, we've discussed all of this before, whether or not you're able to join us. And so sometimes it just becomes you need a refresher, right? We haven't done anything with stats for 9, 10, 11 months. So hopefully this will be useful in that regards as well. All right, let's dive in here. So we'll start way at the way top from a very broad perspective. Of course, the goal of research is we're trying to determine whether our treatments of interest perform differently. And of course, your choice of treatments, they could be different products, different formulations, different rates of application. It doesn't really matter. We just want to know if those treatments can be distinguished from one another, whether it's in their effectiveness, the safety to the crop, or the cost, or maybe we're hoping actually the performance is indistinguishable because our product is cheaper. All sorts of combinations. So of course, then we go out and perform research trials to obtain a bunch of observations of what happens with those treatments. In ARM, we usually call those assessments or ratings. And so the question is, are the differences that we observed due to the treatments, or did it happen just by random chance? And so that's really where statistics comes in. Namely, we're going to use the analysis of variance. But before we dive into the analysis, it's important to first confirm the data. So after you've recorded it, let's confirm what's going into our software for those data points. We won't catch any outliers or issues with the assessment. So that way we have, we can be sure that our data is accurate before we start the analysis. So, the best way to ensure accuracy would be to review the assessment immediately after taking the data. So while you're still at the trial site. That way, any value that doesn't seem right, that seems pretty irregular, can be investigated and resolved because you're still there. If we just jot everything down on a piece of paper and we input and look at the data next time, next rainy day, or even just back in the office later that day, there's nothing we can do when you spot an irregularity. Best you can do is just drop out that data point, which ends up causing a loss in statistical power. So that's really not great. That's why we've got kind of a variety of tools in ARM for and some of our data collection tools to be able to do that on site right away. And so the oops, missed that bullet point. The issues we're looking for, it's sometimes just a typo when we put in the data. Or it could be an outlier, which is an observation that lands outside the normal or expected distribution. Just another thing you could do as far as data accuracy goes would be to identify an acceptable range of values before even taking the assessment. So that way, like in extreme values kind of stand out during note taking. Wait a minute, I was kind of thinking it would just be between 20 and 40, and suddenly I've got a 55 here. Wait a minute. And that can cut down some of the surprises when you're done taking the data. So let's look at the tools in ARM. These screenshots are from ARM. It also would translate into our tablet data collector tool, which of course just is ARM plus a few more features for a tablet screen. And then we have an equivalent for ARM mobile if you're using the mobile app. Either of those options, again, just with the idea of data collection, that's the time to do this step. So primary tool, I think, for confirming the data would be the assessment map. Pretty well kept secret in some regards because you really only can find it over on the properties panel when you're looking at the assessment data editor. So over on the right under properties, there's a little box with tools and a button that says assessment map. And that creates a heat map to visualize the assessment, that assessment column that we are in. So the colors are just based on the smallest and largest values recorded in that column, trying to make it easy to spot any extreme values, high or low, in the assessment. So here on the screen, pretty loudly, we can see that plot 904 is quite a bit different than everything else, right? So that's the hope, is just to have oddities stand out, whereas just a list of numbers sometimes not so much. And if I can get that to pop up, if we then go and kind of look at the data itself, then we can see that plot 904 is 120, which actually for this assessment isn't even possible because we're doing percent area of our leaves that are diseased. So it's impossible to be 120. So we know that's a typo. Of course, the question is, what can we do? Again, kind of hammering home why, if you're at the trial site, there's very significant advantages, because if we're just in the office staring at this 120, what can we do? It could be a 20, it could be a 10, it could even be a 12. We don't know what it's supposed to be, other than we know it can't be 120. And so we can go back to the plot, make sure we get the right value recorded. If we don't, then we just have to throw that out. And there is a checkbox to exclude. So you can at least keep the recorded value for whatever purposes that may have, but then you basically cross it out so it can be included in the analysis. Which again, it's really a missed opportunity, and it's gonna have kind of a pretty, depending on how many you end up with a negative result here, just in the statistical power when we get to drawing conclusions here in a moment. Oh yeah, there we go. So just kind of carrying through, if I had my ARM open, we'd say, okay, well, let's say we can resolve that number, right? We go ahead and confirm that, yep, that is a 20. We can walk back to the field. You can tweak the 20, bring back up the assessment map. So that's kind of nice in the software once we fix things. So now I've generated a new one, which actually shows us a lot more detail, because of course we don't have that one very extreme value that kind of washes everything else out. Also, this screenshot looks quite a bit different because I've turned on the show true scale option. You can see there at the bottom. Kind of another handy way to really map out the true spatial effect of the map. So we draw each plot according to the dimensions in your trial settings. And you can even have the alleys. In this case, I have no alleys, but if you have the alley setting, everything is really drawn out to try to match that, which hopefully just gives you an idea even more so of the spatial aspect of this assessment. And you can also click on a single plot on the map, and only that treatment is colored. So kind of a nice way to compare that product's consistency across the different replicates. Okay, another tool for kind of confirming data and just looking at your data in general would be the Box-Whisker graph. So back on that same properties panel, there's a button to bring up a Box-Whisker. So what we get is a graph with each treatment that has a box and the little whiskers above and below it. The box is your 25th and 75th percentile of the treatment values in that assessment. And then the whiskers extend out to all other values that at least aren't an outlier. So you can look at the box heights. That's one thing to look at. Just the height of each box really gives you a general sense of the variability within that treatment. So a taller box like box 2 here has more variability in it compared to like treatment 3 here that is more consistent. The range of values is closer together. And we'll talk a lot more about that pretty soon here. The box is centered around your median, which is your 50th percentile. And then you can also display the mean as a dashed line. So if you want to get a sense of any skewness in the distribution of the treatment, you can compare those two lines. So for example, this treatment 4, the mean is lower, quite a bit lower than the median. So sometimes you call that the median is the waist. So you have a high waist in some regards on that box, which means there must be some low value in that treatment that's really pulling down the distribution, pulling down that mean. And it's kind of the opposite for treatment 5. And you can see there's an X up here that shows that there's a really large value that's pulling up the mean in treatment 5. And that X is an outlier. So outliers are calculated if you take the height of the box times 1.5, then if a value is farther away than that quantity, you end up with an outlier. So if you hover over that, in my screenshot here now, you hover your mouse over that X, ARM will actually tell you what plot number that is. So kind of a brief talk on outliers. The key with outliers really is that unusual data does not mean it's unusable. So really shouldn't just blindly throw out any extreme value that we see, at least without some thought to it. So really this is where the trialist, your expertise comes into play, because there's quite a few different things to consider when looking at this value that is abnormal in some regards, to decide, should we keep it? Do we need to throw it out? Does this data still fairly represent the trial and its objectives? Did some external force affect the plot disproportionately? Is the recorded value within a reasonable range of outcomes? So, again, kind of another reason, if we can look at these oddities, these strange values before we've left the site, that can only kind of help in this decision making. And here's that screenshot I mentioned about if you do decide, I want to remove that value, there's a checkbox on that properties panel to exclude the value that you've clicked on. So this allows you to still preserve the recorded value, but ARM will ignore it when it comes time to run the analysis. It's also handy. There's a text comment, which would be a good best practice to include anytime you exclude something, to put in a comment to, at the very least, explain the rationale for removing it. And that'll show up as a tooltip as well. So someone who opens the trial later and wants to hover over and go, why did we throw this number out? Pretty nice that tooltip comes in, that comment comes in as the tooltip. Okay, so that puts a bow on step one, just confirming the data. What is in the software, even before we do any analysis? What do we feel good now that that data is accurate, and we're ready to review the data to prepare for analysis. So sorry, we've got one more stop here before we actually do the analysis. Let's prepare it. So we'll first dive in a little bit to lay some ground rules of where we're trying to go. What analysis are we doing? Which in ARM is most usually the analysis of variance, or AOV for short. So statistical variance is a measure of how spread out the data is about its mean. And so what we're doing, the goal of AOV is we're going to break up or dissect the variability in our recorded assessments to try to understand if those differences we have seen between treatments is due to the treatment itself, or if it just happened by random chance. So we have controlled variability that the researcher had a hand in, from your treatment structure, the blocking structure, things like that. Then everything we can't control is your experimental error. And the overall approach is we're considering the observed response really has three different components. There's the baseline response. If nothing had occurred, no treatments were applied, nothing, then the effect that the treatment and blocking specifically had that we targeted to perform, and then the effect of those random influences too. And so if we want to draw conclusions about the treatment effects, then we kind of need to estimate what these random uncontrolled effects are. So if we're going to do that, we do kind of need to make some assumptions about their behavior in order to get a reasonable guess as to what they are. So what are these assumptions that we have to make? The first one is homogeneity of variance, which is just if the variances of the different treatments are approximately equal. If you have a treatment that is much more variable or much less variable than the others, this analysis won't work. So to determine if this is the case, we can look at that Box-Whisker graph and compare those box heights. Or we can be a little more specific and run a statistical test for homogeneity of variance. Levine's is generally the chosen one. There's also a Bartlett's test that can be used. The next assumption is that the distribution of those errors follows a normal bell-shaped curve. So if we have this and equal variances, then all the math can do its thing, because we can calculate a reasonable guess for the amount of error based on that standard bell-shaped curve. It becomes predictable in some regards for us. So a few different statistical tests to really hammer on that normal distribution. There is skewness, kurtosis, and Shapiro-Wilks. Those are the big two. There are a couple more, though, assumptions that do matter. The next one is additivity of effects, which is specifically the treatment and block effects, if you're using the typical RCB design. So, for example, the effects of treatments such as an insecticide are likely to be multiplicative on the population count, affecting a proportion of the insect population. So in something like that, maybe the most suitable assessment to analyze would be a percent of untreated calculation instead of looking at the raw counts to gauge efficacy. So not a black and white, here, run this statistical test, yes or no, we feel good. A little bit more lands on the design, the design of the study, what are we going to do to rate this assessment, and pretty discipline specific, of course, on just what are you looking at, right? Finally, the last assumption is independence of errors, which is that one assessment does not directly impact the next or the previous value. Very, very independent. Again, this one's kind of hard to test for. Usually it's not a huge concern in the ANOVA. The biggest thing is just not to introduce bias in the assessment as you're recording it. Something like an edge effect, or if it's a subjective rating and you have researcher fatigue or something along those lines. That's really where you'd run into problems with the independence of the errors. So that assessment map, that might be your best bet to maybe detect something funky there if that was a concern. So what happens if any of these assumptions are not met? Well, we can't rely on the results of our analysis then, because not meeting those assumptions means none of that math would line up, and we can't really believe what our conclusions would state. Unless, of course, maybe there are some things we can do to try to resolve these assumption issues before we get to the analysis. So there are a few things in our toolbox. The first one would be data correction transformation. So these are designed to correct the underlying distribution of the data, and thus the distribution of the errors as well, without affecting the results. So we do a mathematical formula to each and every data point, so we're not twisting the results at all because we're treating each data point in the same fashion, but then our distribution of the data points is smoothed out to be where our assumptions can do their thing. The math can do their thing. So the three main ones that are used, the logarithm, that's a great one if you have counts of things that occur in clusters, which ends up being a log normal distribution. The square root, things, if you're counting things that occur randomly or very rarely, you end up with a Poisson distribution. And by doing the square root, you end up back at more of a bell-shaped curve. And then arcsine is great for, I think it's the arcsine square root percent is the full name of that transformation. And that's great for percentage values, which sometimes ends up becoming a binomial distribution. Another option would be to use a spatial model, which tries to recover information about hidden variables across the field. We have in ARM, there's 3 trend models and 4 nearest neighbor models. You usually would only do this, though, if your blocking design fails. So it's relatively extreme, I guess, for lack of a better term, in that you wouldn't do it just blindly in any case, but you would want to look at the randomization or your blocking and see, oh, well, maybe we didn't capture the gradient that we thought we did. then essentially with the spatial model, we just throw out the blocking entirely. We give up on that, and we try to kind of mathematically figure out maybe what we should have blocked in some regards. Third option to us would be non-parametric statistics. So we just throw out ANOVA. Let's not even perform ANOVA, because then we can throw out its assumptions. And instead, we analyze the data by ranking the assessment values. The nice thing with that is we still could run a mean comparison in the end, because we can get a mean of those ranks. So we end up with a similar structure in the end as far as being able to compare the treatments, even though the underlying analysis is a little bit different. And the key is we can't fix the assumptions. Nothing else that we've tried up above in this list is working. All right, well, let's just not use ANOVA. We'll use this other statistical test. They're called non-parametric tests. They are a little less powerful, so that's why we don't just do that first. So the ANOVA is, in the statistical realm, a more powerful test. So that's why we try our best first to use that one through some of these options. And then worst case scenario, we can jump over to the non-parametric. All right, so looking to ARM for doing this process, we have the column diagnostics panel, which is to the right of your properties panel. So when you're looking at the assessment data section, it's all the way to the right. And you can see it shows up kind of vertically as a different panel to open up and utilize on the screen. So a couple of different sections that'll show up when you open this panel. The top one provides a variety of basic statistics, or it's like your box score if you're a sports fan, about the column. So pretty basic calculations like the number of values, how many of those values are analyzed compared to what's missing or excluded. Then underneath that, you have the statistical tests for those AOV assumptions that we had talked about. And so the values on the screen, they're in the red square. Those are p-values. So if you have a significant value there in the box, that would indicate there is a problem with that assumption. There's two different columns here. You have a column in the table for each potential course of action or data correction transformation that is being considered in this case. So that first column is titled raw. That is just the regular data points. Then IID, that second column, is the results on the residuals. So that's kind of where we're going to look at. The modern statistical textbooks all say, let's look at the residuals to decide whether we have any concerns about the assumptions of AOV. So it'd be really these four values in the end is what we care about, trying to decide whether any action should be taken or not. Right underneath that table is kind of the other half of this panel. In it is the recommendations table. So for each of those four statistical tests that we're focusing in on, there is a recommendation that ARM can generate based on the results. So in this case, the recommendation is kind of the same for all four of these lines. It's using the IID code. So in actuality, that if you use that, it doesn't actually change anything in the analysis. It's just it's a way to kind of check off this column that I have reviewed the assumptions of ANOVA, and nothing was wrong, right? In this case, there's nothing significant, so there's no concerns. All the assumptions are fitting. We're ready to do the analysis. So if I want to just put in IID in my column, that's just a way to show, yep, I've looked at it, we can move on. So then that way in the future, no one comes through the file and has to look at this again because we've already done it. So in this case, everything is kind of a green light, nothing to be concerned about. So we can move to the next column. So another example with a different assessment where we do have some action that is needed. So we can see with that number 1, the Levine's test is significant. So that tells us that we don't necessarily have homogeneity of variance, and that's a concern. So before we look at the recommendations, you first want to use that basis option there pointed out with number 2. And the idea here is to give ARM a little more context, a little more information about the data that we're looking at. So of course, we've got the raw values that gets fed into the engine, but this basis is a way to give further context for what this assessment is. So by default, you have the assessment values. That's really not giving any more information, but we could point ARM to the rating type or the rating unit or your action codes field to tell ARM the type of data this is. So in my example, this is count data. And so by changing to rating type, you can actually see that sometimes the recommendations actually change. So ARM kind of knows the mapping of, oh, well, if this is count data, the square root form, the square root calculation is kind of the preferred method. So let's look to the square root and see if that fixes our problem. And I won't even bother looking at some of those other transformations that might not jive as well with count data. And so sure enough, then we end up with the square root. That's the recommendation. There's step number 3 that says if we run the square root, we can see up above the p-value is no longer significant. That does resolve the issue where our variances were not equal across the different treatments. So you can double click on that recommendation on the screen, and what happens is then ARM puts the AS code into the ARM action codes field for that column. And really what this is simply instructions to ARM later on. When we run the AOV analysis, then we have this action to tell ARM first, before you do the analysis, you need to run the square root transformation on these values and then do the analysis. So you'll notice that the values themselves in the editor are never changed. We would never change the data. We just want to put down an instruction for the analysis engine later on. Okay, one more example here that's even messier than the last one. So if we look here, really none of our data corrections saved the day for us in this case. So if we look at like the Shapiro-Wilks, both the Shapiro-Wilks and kurtosis, doesn't matter what we try, the log, the square root, the arcsine, none of them recover. We can't fix this normality issue no matter what we try. And therefore, in our recommendations, we end up with AR. And so that is the rank transformation, if you will, basically turning on that non-parametric statistics. Again, the idea is instead of means and standard deviations in the analysis, let's rank the data and do an analysis on those ranks instead. So we can add that AR action code, again, just to this one assessment, which is nice. All of the other assessments that fit nicely with the AOV assumptions, we still will get to do the ANOVA analysis with those. It'll just be the particular ones that don't fit those assumptions that this other analysis will happen. So pretty handy. We still end up with those rank means so we can still perform a comparison. So actually we'll always still run the same report in the end. Okay, real quick, one other tool on the diagnostics panel, if you want to take a deeper dive into the data, there is the Show Graphs button. And that draws a variety of diagnostic graphs that really are trying to help visualize the data and the specific things we're looking at, right? So here I have a graph for the Levines, essentially, trying to visualize the variation. And then you have a QQ plot for your Shapiro-Wilks, again, looking at normality. The spread location gives you a sense of skewness, and then a histogram for the kurtosis. And then left and right, you usually have the assessment itself without any transformation. And then on the right would be whatever proposed transformation that's recommended. So you can kind of compare before and after, what are we going to do? Okay, so again, that's kind of the main tool for data review, and just kind of step through each column in your trial to make those decisions and put down the actions in the action codes field. Okay, so moving to step 3, let's actually talk about the analysis itself. So I'm just going to maybe step through an example. We'll just say it is from some trial. We've got some harvested yield information. There's 5 treatments in this study. We ran it across 4 different replicates. We'll just kind of talk through the calculations quick of what actually happens in the AOV analysis. So we end up with this table. That's kind of the standard end result to display what is happening within that AOV analysis. We'll just kind of go column by column on how these are calculated. So first one is your degrees of freedom. A little hard to define, but it's the number of values in a final calculation that are free to vary. So with variance, that's our focus here, the degrees of freedom is n minus 1. So for treatments, if we're going to look at the treatment variance, we've got 5 treatments, so you have 4 degrees of freedom. Or another way to look at would be you're taking 1 away because the mean is calculated in order to calculate your variance. So a few different ways to look at, but that's what you end up with, how you calculate degrees of freedom, just n minus 1. Then we do sum of squares. That represents the amount of variation in the data. Again, we are splitting that up into each source that's listed in the table. Then we can calculate the mean square, which is the sum of squares divided by degrees of freedom. So we're taking the amount of variation and dividing it by the degree to which it can occur. Then we can calculate an F ratio, which would indicate the level of variation from that source compared to the random variation. So of course, the larger that ratio is, the stronger the signal, right? The more likely that the variance from that source is not due just to random chance. So we're taking like our treatment mean square, divide that by the error mean square. Look how much stronger did we have variances coming from those treatment responses. In this case, it's about 3.5 times as much. So it gives us an idea. That's seems pretty good, right? If it was neck and neck, if it was pretty much the same, or between blocks we had even less. There's less could be explained with blocking compared to the error that we have no idea. That's pretty weak, right? Well, to try to formalize that instead of just going off of vibes, we can calculate kind of the last value here, which is a p-value, the probability that the observed differences in treatments or maybe block, depending on which row you're looking at, the probability that those could have arisen by chance. So a low p-value would indicate that we have a lot of confidence there are real differences. In this case, we've got that 0.04 among treatments. So we have some confidence there. This didn't happen just by random chance. On the flip side, if you have a high p-value like this, 0.6, there's really not a lot of evidence of real differences between our blocks in this case. Now, this could be because there is no difference, or that the differences are just too small for us to detect, depending on how much, again, statistical power that we've got as we're doing this. So lots of numbers. We'll try to avoid too many more numbers. But to summarize, ANOVA, our AOV is breaking apart all of the variance in our observations into different sources. And then we calculate a p-value as kind of the end result. And that p-value is a probability. And the AOV p-value is the probability that no differences in treatments exist. So that p-value of 0.04 means we're 96% confident that there are significant differences between these treatments that we're comparing. But we're not done yet. We usually want to know specifically which differences are significant and which are not. So after AOV, we want to run a mean comparison test, because AOV itself doesn't tell us specifics on which treatment was different from which. It just gives us an overall idea of, is there something here or not, essentially. So we then run a mean comparison test, or also called a mean separation test. Again, we're going to actually compare each of those treatment means against each other to figure out which ones are significant and which differences are too small to be considered significant. So there's a variety of different tests that you can run. And ARM has quite a few options. The most common ones are kind of these top four: LSD, Duncan's new MRT, Student Newman QLs, and Tukey's HSD. You also have to choose a significance level or alpha to run these tests. It's related. It's similar to the p-value for our confidence in AOV results, but really it's setting the threshold for significant differences for the test. So an alpha of 0.05 implies that we're only going to accept differences that have a probability of 95% or higher of being true. So it's important to make that selection ahead of time prior to running any analysis, because that choice really shouldn't be biased by your desired outcomes. We don't want to peek at the data and go, okay, well, we're 92%, so let's run alpha at 10 and we'll see what we want. You want upfront to say, this is what the objective is, this is how confident we would want to be. Now let's run the results and see what we get. Of course, the big question then is how do I pick, right? Between the tests and the alpha level, there's a lot of combinations, a lot of choices to make here. So few different perspectives, I guess, on this, because of course this is statistics. There's never just a straightforward answer, right? It's all shades of gray. So let's start by classifying the tests. So those different tests, you can really classify them by how liberal or how conservative they are. So that really means tests can be more likely to report a false positive, which is called a type 1 error, or more likely to give you a false negative, which is a type 2 error. So the first four tests listed in ARM are arranged from most liberal to most conservative. So again, the liberal LSD is the first one in the list. Then that LSD is the most liberal test, and so it's most likely to report differences between treatments, but it suffers from the fact that it does have a higher false positive rate. So hey, cool, I found differences, but there's a chance it's telling me there's a difference when in reality they aren't that different. And then on the flip side, you can be, very confident in any differences you see with the conservative Tukey's HSD. That's kind of the bottom one on the list. But the downside again is you're less likely to see separation. And so there's a higher chance of that false negative where we didn't see separation that really truly is there. Right. So it's all on a scale trying to balance those two issues, I guess, what you're trying to do. So other considerations to try to make this decision, of course, just following industry standards or discipline standards is a good way to go with too. Everyone just collectively, it seems like everyone uses this kind of test in my industry or in this with this type of product. Everyone runs Dunkin's or whatever. That's a good starting point as well. Or if you're running a sponsored trial, the sponsor might have their own opinion. Please run this. That, of course, makes the choice easy. You could also should consider the purpose of the study. If the trial is part of the registration package, then a conservative test is appropriate. But on the other side, if we're just in a screening trial, that's all about potential. So a more liberal test might be preferred because any false positives will be weeded out in future studies. So you're just trying to find any possible differences to proceed with the next set of trials next year. So another thing to help try to balance those scales. Finally, the penalty of failure is another thing to consider. So, for example, the failure of a crop protection product is very likely to have an impact on yield or the end thing we care about in the field. So that's really where like your alpha level of 5% is very common. We want to be really sure. But if you're testing a biological product for plant health, the penalty of failure is just the cost of the product. right? You just didn't get the boost that you were hoping to get, and you had to pay money to put it on your field. So much lower penalty of failure there. So, a 15 or a 20% significance level, it can be perfectly appropriate for those types of products. Um, it all is just the just the math of it all of what is the proposition of this product in the first place. So a lot to consider, a lot to balance. Like I said, unfortunately, there's no easy answers, right? In the statistics world. All right. Let's just go kind of real quick through a mean comparison test. We'll try to go fairly quick so we can get all the way to the end. We're almost there. Um, the specifics as we go through this, the specifics for each test is of course a little different on what gets calculated, but the basic concept here I think fits for all of them. So I think it's useful to step through. So we'll be doing the LSD mean comparison here. First step is to calculate a test statistic, and that's going to be used to perform the comparison of means. So here with the LSD, the calculation comes out to 5.49 for that data that we were using before. Then what you do is compare the largest treatment mean to each of the other means using that test statistic. So I like to imagine it as basically a ruler. That test statistic 5.49 is the size of our ruler, and now we go measure up the treatments to compare them. If the difference between two means is smaller than that LSD value, if they're closer together than our measuring stick, then we can't consider them significantly different. And we can't detect that they're different. They're too close together, right? So trying to visualize this process, I'll use a number line. And really that LSD value is going to create a range around each mean. And anything outside that range is significantly different, at least according to the test. So again, let's start with the largest mean, and we can extend to the lower bound using that 5.49, right? So all treatments within this range are not significantly different. So we assign the letter A to treatments 5 and 1 and 4. Then we can repeat this process for each mean. So looking at number 1, there are no new means in this range, so we don't really need to use a letter. It's the same list, right? The next range does include treatment 2. And so treatments 4 and 2 are given the letter B because they're in their own group. Moving down, the next range is treatments 2 and 3, and so we give that range the letter C. So there are no more means that don't have a letter, so we're done. So the letters then we usually just report right next to the means themselves, just like that. So that's kind of exactly how a REM will present the results then on the AOV report. So treatments, of course, we do a little more than just treatment number 1. Put whatever treatment details, the name, formulation rate, whatever you want on that report for each treatment gets filled in. Then for each assessment column, we list the treatment mean and those significant letters. That's kind of, if you skip to the end, that's the result, right? That's usually what you care about, is what differences did we see. Then underneath that, kind of all the statistical values that came along for the ride that you chose to calculate end up on the report. And there's usually footnotes to kind of explain what all was done here, right? Statistically, what mean comparison test, what alpha level, things like that. Okay, well, we made it to the end. So just to recap, the AOV analysis is all about breaking apart the variance in our observations into different sources. And we turn on, do some calculations, and calculate a p-value probability at the end. Then we perform a mean comparison test to determine which means are significantly different. But of course, before you do that, you got to be cautious with the analysis. If the data doesn't fit those assumptions that we talked about, we can't trust the results. So that's why all those tools for data confirmation and data review are important to step through with your assessments before you run the analysis. We didn't really have time for any frequently asked questions. That's usually kind of the fourth in our series. So again, I would just kind of close with a wrap up of an invitation for hopping out to our website. Like I mentioned at the beginning, pretty much everything we did today would be videos 1, 2, 3, and maybe a little bit of 4. You could certainly probably hop on number 4 to actually we talk through what's on the report and how to generate it and a few options. That's really kind of right where we're leaning off here or finishing up is that AV report and then some common questions. So in that video, we talk through most often what we see in our support box of, hey, I've run the analysis, but I'm confused what it's giving me, or it's not doing what I thought it would, etc. So those might be useful resources to carry you forward from where we're leaving off. But with that, kind of taking a victory lap that I didn't get too long-winded, which is a miracle. But hey, we kept it in PowerPoint. That's my trick to myself. Once I get into ARM, I just start rambling. I get too excited and talk too long. So we made it under an hour. Of course, as you're going through and running your statistics or doing that data review, if you have any troubles, as always, feel free to reach out to us or your local representative, and we can help you out. So thanks, everyone. And hopefully we'll be seeing you at another webinar soon.